words. I'm not trying to tell you how to use words, but I'm suggesting that there are terms out there that are worthy of investigating. For example, as Terry said, I mean, every time somebody says, oh yeah, I can see the hologram. It's not a hologram, but we can't be like King Canute and turn back the tide. Say, no, they're not holograms. They're virtual seen objects. But I guess hologram is better. All right, here we go. The reason for thinking about these three processes that you will want to go through is part of design. That you will want to say here, we're designing systems, and therefore, what is a system? The systems are things which are put together to stand on their own. System. Sin is bring together, stand on your own, put together. Now, every system on the planet, whether it be biological, whether it be engineered, if you walk across the beach and you find something, you find a virus, a COVID virus, or you're investigating an engineered process. Leo, you're going to love this part because we argued, we had fun with this at the restaurant. When you go to talk about systems, there's really just to characterize the aspects of a system. It's about the inputs and the outputs. Systems have inputs and outputs, but they also have two things. They have structures, architectural structures, and they have behaviors or functions. And one might say, and all that other stuff, but I believe it's important to say that systems only have those two things. When you go to come up with theories or representations of those systems, and remember, this will be about the medical augmented reality system that you're going to design. But anyway, this is true of all systems on the planet, that when you have representations, whether they be informal or formal about the system, they can only be about their structure and about their behavior. Controversial or not? Many people say, oh, that's trivial, that's Leo. Other people say, there must be other things, right? But there's not, okay? So if we just take that as an assertion, we now begin to think about design of human-computer interfaces. Any augmented reality system, whether it be for interventions or whether it be for trainings, is in its very nature a human-computer input system, a HCI system. So I'll be trying to be specific to augmented reality medical system, but everything I say is going to be true of HCI. This is just taken from my HCI grad course, right? So the name of the game in design is to come up with representations for the system that you want to design. And those are conceptual representations. That was the idea forming process that we went through. It's tricky, isn't it? It's really, really tough to try to envision and to describe a system. But this notion of synthesis is to transform those abstract concepts into physical instantiation. That's what engineering is all about. The enterprise of engineering is about going from informal to the most formal. And when I say formal and informal, take informal. Who thinks, let me look on chat, who thinks that informal means kind of like approximate? No, informal merely means that when you describe something informally, perhaps in spoken English, that grammar doesn't matter, that syntax doesn't matter, that the semantics of your design can be captured informally, but it is syntactically correct. Sorry, I misspoke. It is semantically correct, captures the intent of your design. And then as we try to move downwards into the physical instantiation, I'll argue that you're going to create design artifacts. You're going to create blueprints. You're going to create code. You're going to create sketches of these things. And that process will be about the direction that we go for engineering. Synthesis is to bring stuff together. Bring together. Thesis, an idea. Bring together the components of an idea. Analysis is the opposite direction. Analysis is when you have a structure that's put together and you begin to take it apart. That's what Lysol does, lysis. And that's a different direction. And it will turn out that those three things that are the start of my talk title is the scientific direction. Okay, that's going to be the main punchline. So we might be software engineers. We're building a piece of software. Much of your system will be like a software system. Quite a chunk of your system could be a physical system. Depends on how you deploy it onto physical devices. But for software engineers, this stack of levels is usually quite obvious. If you just consider a representational framework like UML. UML is a set of diagrammatic formalisms. It's a framework for capturing system representations from informal to formal. So that software engineers are quite comfortable with this kind of a diagram. And now the thing about engineering is that it's a methodological process for design. And that's what you'll want to inject into your reports. You'll want to show the systematicity of the way in which you conceptualized your system and you brought it into fruition. And as you all know, there are many different mappings between what you want to do and what you might implement. So there's a one-to-many mapping between these concepts and the physical instantiation. So in other words, if it was synthesis, that would just be a one-to-one mapping. That's a direction. But in fact, what we do is we know that there are many mappings, one-to-many. Any one of those systems will satisfy the requirements. But if we're being methodological, if we're being engineers, or if we're just being formal, we will have reasons to choose one from the other. Might cost less, might be more ergonomic. It might be more efficient in terms of power. But whatever criterion you decide to apply, any one of these may still satisfy the requirements, okay? But choosing one of them to designate one of those paths, designato, the Latin root, that is the root of design. It is to choose one of many from this path of going from concept to implementation. But let's move on because, in fact, it's the other direction that I'm here to talk about. The important question, no matter which you call it, of those three, Fubar and Baz, Alice, Martha, and Mary, the question on the table becomes, does the implemented system match the specified requirements as broadly as you wish to scope that question? So there is a very precise and narrow engineering sense in which we can say, does that implemented system match the specified requirements? And the answer is pretty binary, right? It's yes or no. And it can be yes or no for each individual component that make up a system. And that's called verification. That's engineering verification. Did it meet specs or not? On as large a list, there should be a large list if the system is complicated. And that can include unit testing in engineering. So although I'm saying that this is science, this is the direction of science, that's where you have an existing system and you try to come up with theories for how that system is either structured or behaves. And then you take that theory and you compare it to what was specified. And you're doing a diff, you're matching the two. Are you in that scope? Yes, then that was verification. Engineers sometimes call that unit testing. So you see, engineers behave scientifically as well. These are loops. This analytic synthetic directions are iterative loops of design. And you all know that as you're trying to take your ideas and build systems. My encouragement is that you capture these loops of design. Say when the system wasn't working, say what worked. That's going to lead to a great report. All right. Are you ready to be interactive? Come on, summer school. Let's see your interaction. Here is a quiz question. Use Zoom chat. I'm watching you here. Wait a second. I think I went, did I go too fast? Yeah, okay. Well, no, okay. So this is a question that software engineers will say. What kind of representations are in a system requirement specification? And please feel free to Google it. Because you know what? When my students are writing their exams online, they've got Google. I know they've got Google. And so how could you get anything wrong? Well, what goes into an SRS? Everybody's watching the chat. What are the major categories of representations that are in a requirements document? That's okay, I'll wait. You're not being very chatty, are you? Matthias hasn't even answered yet. Come on. Alex has no idea. Come on, Alex, you sure have an idea. You're just messing with me, man. I know you better than that. If you Google system requirement specification, you will see it's a document that contains the functional and the non-functional requirements. Don't. What else could it contain? I could say, hey, it should contain the blue and the non-blue data. Not specific enough, Matthias. Who, man, you got half the picture, right? Sure contains structure, sure contains behavior. I don't know if I let the cat out of the bag, but you know that the classical answer from Google is it contains the functional and the non-functional. Now that is so tautological that it's not useful. Now, if I'm trying to advocate a dichotomy which serves us much better, is it not behavioral? When we say functional, that's input and output. But all of these systems have inputs, outputs, and states. They evolve over time. That's an interesting human-computer interface. That's a surgical workflow. The inputs and outputs are changing. The mapping between inputs and outputs are changing all the time, and it depends on state. And so that's what you need to represent in your behavioral description of your system. When you're describing a medical augmented reality system, whether it be for diagnosis or whether it be for an intervention or whether it be for training, you're going to be talking about the inputs from the human, the outputs to the human, and the way in which that system or process evolve over time. So anyway, that's not just functional input output, but that's behavioral input output and states evolving over time. So that's what I mean by behavioral. And now, if I want to be tautological, I would say, okay, so you have to put the behavioral requirements in, and you have to put the non-behavioral requirements in. What the hell is a non-behavioral requirement? Tick, tick, tick. That's okay. I'll wait. What's a non-behavioral requirement? Human got it right off the start. You already had the right answer. It's structural, the structural requirements. Now that's okay. We can all take that. But here's the controversial thing to say. There are no other ways in which you can specify the system than those two ways. Put that out there. I'm happy. I tell my students, come up with another one. I'm going to give you 100% in the course, no problem. And summer school, I'm going to give you 100%. There'll be cash prizes awarded. That's not a mathematical proof that it's only structure and function. I know Leo is already saying, oh, it's so obvious. That's so obvious. But for those of you who have not heard that before, that is a very, very important characterization of what we put into design documents. So now an important question. Of these two things, which I'm stating are the only straws afloat, can either of them be analyzed without the user performing a task at the system? Chat. I'm looking for chat. I'm looking for yes, no. That's all I want. Yes or no. Or actually, the question is more than that. Can either of these, can the behavioral or can the structural, let's start with structural. Can structural be verified without the user? Yes. Can behavioral requirements of the system be investigated without the user? No. And the user must be performing the task that your system was designed for. So Jonathan Knopf quite amazingly remembered my talk from 2 years ago. That was basically what my talk was about, that the user must be performing a task in order for you to do the sense of analysis of your system. Now, everybody who's eaten in a restaurant with me knows that I like things that come in small numbers, sets. So there are exactly two categories of ways that you can make measures of systems. This is so pertinent to HCI, to the analysis of augmented reality systems. There's subjective and there's objective, and there is no other, okay? And what's the difference between subjective and objective? Checking out the chat. Who wants to take a stab at it? Remember, there's cash prizes. Difference between subjective and objective measures. Thank you. Subjective depends on the user, but so does objective. So that's a thank you for that answer. But both require that the user performing a task. Getting closer. Objective is measured with numbers. A better way of saying that, if you don't mind me kind of rephrasing, is that objective is something that you can measure and it will have units. Will be physics-based measures, okay? Whereas subjective is what? It relies on people's opinions. Opinions is what you get when you get subjective responses, okay? Meg is saying, can have multiple answers. Yeah, if you ask somebody something subjectively today, they might give you something tomorrow. Whereas the dimensions of an object are the same day after day. They can be checked, they can be calibrated, but subjective answers cannot. So with that, I just got 3 slides to piss on subjective evaluation, okay? Sometimes, now let me be upfront here. Some things cannot be measured objectively. And these are what W.V.O. Quine called qualia. Things which are in our head, things in our imagination. Those things can only ever be accessed by asking a person their opinion. Okay? And there are some things in HCI that have that flavor. But whenever you ask a person their opinion, as in formal studies, the problem is you have 2 cognitive systems in this equation. You have the experimenter and you have the subject. And if the questions are subjective ones, you get biases on the experimenter side and on the subject side. And if you Google cognitive bias, you'll get a Wikipedia page which has 100 cognitive biases. There are lots of them. But there are classic ones that I can put in my HCI courses and ask exam questions about. And they're good ones. So a short set to just give you the flavor and to really kind of try to focus on the common ones that taint subjective evaluation. Placebo effect, that's a cognitive bias. That's where if you're trying to test whether this treatment for COVID it will cure you, you have to do the following. You have to give them or headache. You know, let's go to the Swiss Bayer aspirin. People report that they have a headache. Now notice that's entirely subjective. You can't measure headache. You can just ask people on a scale of 0 to 10, how much pain are you feeling? And then you try to treat them and you give them your drug, and you have to give half your population the treatment and you have to give half the population placebo. Because even when you receive placebo, you will report that you feel better. Now, to test whether your treatment is significantly different from placebo, because there will be a placebo effect with the treatment, but you want to test whether it's significantly better. Hey, professor, what does this have to do with augmented reality? Well, it has everything to do with augmented reality, because if you want to test your augmented reality system, you're going to have to do controlled experiments and see whether the task is facilitated by your treatment, your innovative new ideas in augmented reality. Okay, so we'll go quickly. Novelty effect. If I show you a system that's the old way of doing it, and I show you a system that does exactly the same thing, but it kind of looks new or it feels new, that's the novelty effect. And you will report or you will behave in an enhanced way on those new devices. Halo effect. You know, I think this is the biggest one in subjective studies of augmented reality systems. Halo effect is this idea that if you associate the system with the person who is performing the experiment, and if that person is reasonably attractive, by attractive I mean opposite of repulsive, you don't want to run away from them. It's nice to spend time with that experimenter. The entity that they're testing will have the halo effect, will seem better. Kind of related is the Pygmalion effect. This is where the sculptor created a sculpture and fell in love with it and could see no wrong with that. So whenever you're in a study where the experimenter comes to you and says, "This is the best thing we've ever made. It's great, it's fantastic. I'd just like to ask you a couple of questions to see, what do you think about this thing?" I reckon, you can call this Eagleson's approximation, is that if you have a system, a new system, and you've got a reasonably pleasant experimenter showing you that system, you're going to get 5.2 out of 6, no problem. It'll be 5.2 out of 6. It'll always be 5.2 out of 6. So Pygmalion effect is the opposite. That's when instead, you know, you could do an experiment. You could have a nice, you could have a happy grad student and a grumpy old professor. And I show up and I say, well, students have really done a bad job on this thing. We've been working on this for years and years. And I know it's been COVID, but look, check out this augmented reality system. We're doing our best here. What do you think? What do you think is going to happen to this subjective evaluation? That's the Golem effect. And the Hawthorne effect, for any of you who want to go into a career in user experience on these kind of augmented reality systems, you better know the Hawthorne effect, because you'll want to say this in corporate board meetings to show how bright you are. This is the Hawthorne plant, Western Electric Company, just outside of Hawthorne, Illinois, that Mega is saying, should we be worried about this? Yeah, we better be worried about this stuff. This is why I'm standing up here chatting, being so chatty about this stuff. Because I will want to quickly dispense with subjective evaluation and move to objective. That's exactly what I'm about to do. But we need to tell the Hawthorne story. Hawthorne plant was one of the places where operations researchers tried to engineer optimality out of their workers. And they tried different treatments. They tried to paint the rooms green, other than that other crappy color. Or mess around with the lunch breaks. You know, instead of one big lunch break and a couple of little bathroom breaks, you expand them into being larger morning and afternoon breaks. When they do that, they find the output of the plant improves. And then if you try a different treatment, the output improves again. And the output improves again. And then they go back to the first condition and the output improves again. Like, it just didn't make sense. And they realized that what was happening here, and this is what the Hawthorne effect is that when a population of users knows that they are being studied, their behavior will improve just because they know that they're in a study. Now, I don't know anybody who I've ever done an experiment on who didn't know that I was observing what they're doing. Anyway, there you go. I hope I'm not pissing too much on subjective evaluation, because it's clearly important when you're trying to measure qualia or opinions of people. For example, satisfaction. There's not a physics-based measure on the planet that tells you somebody's satisfaction. You can only ask people that. And that's ostensibly something about human-computer interfaces. But now, if I may, let's push that aside and we move on to objective measures. Oh, well, no, I misspoke. You know, here we've got, it doesn't take much Googling to see that people believe that if you want to measure how good a user interface is, this web page says, just ask them a question after it. Like, how difficult was that task? On a scale of 1 to 7, how difficult was it? You don't think this is going to be corrupted by cognitive bias? One question? All right, so don't do one question. Let's do more than one. Here's a Digital Equipment Corporation in 1980. Came up with this kind of a survey that you could ask users. How did you like it? How did you feel? And there's this kind of a sentiment that when you give this survey to 100 people and you take the responses and you average them, that's somehow an objective measure. It's not an objective measure. It's just an average of subjective measures. And then our favorite. This is for you, Eddie, right? The NASA TLX. You see it all through our literature. NASA TLX. So many people don't even know what it looks like. It looks like this, right? Those are the questions. And there's this some kind of notion that we're getting an objective measure. It's not an objective measure. It's all opinions. So that's NASA TLX. So I guess did I say I would try to be kind of even-handed and balanced? I guess you can see my bias creeping through here, that when we are trying to measure something about a system, which can be measured objectively, we owe it to the design process to do that. So we cross the Rubicon now and move on into objective evaluations, okay? Now, we've all agreed that you cannot objectively measure the usability of a tool if there's no user and there's no task being performed. So this is essential to objective measures of performance. And those tasks can be any task. They can involve interventional tasks. They can involve diagnostic tasks. They can involve training tasks. All of these things have objective measures associated with them. So let's see, where's my quiz question? Well, here it is. I'm ready to look for you on quiz. Here's the party game that we're going to play, summer school. okay? Each of you has a project, and at the core of each of those projects, you're coming up with a task. And nothing out my sleeve, presto, I'm doing a card trick here. I don't care what task it is, and it doesn't even have to be medical, but can you please come on the chat and tell me some objective measures that you can take that will address a question about the performance of that user on that task. Ready? Here we go. Looking on chat. Getting some fantastic answers. Accuracy, time to completion, number of errors, task time, speed, rate of errors, speed. I love you all so much. This is going great. But now, because Augmetics couldn't make it here, we have an extra hour. I'm just going to stand here and I'm going to wait until you tell me something other than speed and accuracy, something other than time and error rate. Somebody come up with a different one. Patient outcome is a good one. But we're now user acceptance, subjective, right? But we're starting to see, and it's Meredad who says it. So God bless you, Meredad. There are only two. There are only two: speed and accuracy. And Merle will you know, in her talk, you see that when you look at experimental psychology, if you ever read through the literature of experimental psychology, you wonder, like, how come they're only just ever measuring time and accuracy? Well, because that's all you got, and it's the same thing in any domain. And there are some comments in the chat, like patient outcome, and thank you, Eddie, for that, but that's going to come out in validation. So where I'm at now is that there's this notion that a human with a system can have their performance evaluated for any task, as long as that task is well specified, so that you know what, it must be a well-posed task, that if you have a well-posed task, then you have this notion of what should be the correct interaction and how long or how quickly could they perform that task. And that's all you got. But that should be called something. And it should either be, this is the B of my three. This is the foo, this is the bar, this is the Martha. And the hard one that comes later will be the one that we're supposed to call validation. That's what we're supposed to call validation. But in many papers in our literature, validation has weakened to something which is more about verification or about evaluation. So here we are in my talk. We've just talked about evaluation of performance. And now here we go for validity. This is the point at which I could start to pull up and share the kinds of studies that we've been doing. And I do have a bit of time to do that. You'll want to see some pretty pictures, right? Let's back up a bit. VR perception workshop. Oop. Trade that off. There we go. Dun, dun, dun. No, that's Sandrine's talk. Here we go. AR, VR. Am I sharing? Good? Good. There we go. These tasks that we are asking people to perform are human-computer interface tasks. Therefore, they will involve humans, and that human is being, that human mind is the software that's running on that physical thing called the human brain. And if you just look at the architecture for that human brain, you look around and you see that, you know, roughly the back half of the brain is dedicated to perception. So there will be perceptual tasks. There will be aspects of a task which are about perception. And a lot of the concerns that we have in AR are about whether the scene has been perceived veridically, okay? Has it been perceived in a way which is useful to the user? And that has exactly two implications. Has that scene been perceived in a way that it can inform the cognitive system, that it should believe certain things about the world? Cognitive system is about goals and beliefs. And the other way in which the mind and brain work is that that perceptual system can have direct links. Our colleague Mel Goodale has made his whole career about this notion of the two channels of the visual system. But there are direct links between the human perceptual system and the action system. So the inputs can be used to guide outputs, to be sure. That kind of interaction can be measured using accuracy and performance. But the notion that what we see can lead us to believe something, whether it be diagnostic, whether it be about the intervention, or whether it be about training. You know, I now believe something about how I should interact with surgical tools. That all that real estate is the cortex. Got the perceptual system, huge. The reason why the perceptual system has so much real estate is that the bandwidth is so high. You know, visual imagery, auditory, touch, kinesthetics. Sure, there's smell and taste, but they're non-starters in AR as far as you know, for argument's sake. But that they're channels to feed the cognitive system where we think about the world, and these come back, and the outputs come through this motor strip, where the motor cortex, the cognitive system is saying, I have goals and I have beliefs about how I will act and interact with the world, and that they are played out across that central sulcus, where on the sensory system side, there's this beautiful, it's not coincidental, you know, the places which control the digits of your hand are just right there beside the places which your touch receptors of your fingertips are. There's a project where it's about tongue input and output. The places where you control your tongue are right opposite the places which in which the tongue is sensitive to touch, etc. So it's all input and output right along that strip, input-output systems. And now the question is, with all this great architecture here, what kind of inputs can our augmented reality systems receive from the human? And this is another quiz question. I'll put a finer point on it the way I asked my HCI class. I'm usually asking this question about 2D interfaces. How many different ways can the human interact with a computer? But everything I say about windows, icons, menus, and pointers, completely true of augmented reality interactions and virtual reality interactions. There's nothing different here. How many different ways do humans have of interacting with computers? Looking on chat. If you go to your, I was going to say Best Buy, that's North America. What's the European version of Best Buy? Interdiscount. You go to Interdiscount and you say, hey, I'm interested in buying some input devices. Say, okay, it's over here in this section. And you walk around, and I ask my students to take pictures of these things. And I ask them, how many different kinds of things are there out there? There's buttons. And there's sliders and knobs, pedals, right? And there's position trackers. And there's keyboards, or there's voice recognition microphones. And are there any others? You already get my style of lecturing. There are no others, right? Position, quantification, selection, quantification, position, and text. There are no others. There are no others in laptops. There are no others in the 1960s. There are no others in 2021, virtual and augmented reality. There will be no others ever. I always try to say things which are true, independent of time. Now, how can I have the audacity to say that there will only be those kind of interactions? Selection, quantification, position, and text. What is it that constrains the space of computer input devices? Is it engineers' imagination? It's exactly, Matthias he's going to get the cash award right now. It is exactly the space of human outputs. See, that's why I draw this schematic. Anything that's a computer input in an HCI system is a human output. And what do we have for human output? Because you're on a roll here. Yeah, how many different ways does a human have to output stuff? One. Muscle. That's all we got. That's all we got. Everything we do, even my speech, it is, the speech that's coming out. So I can move my muscles as an output system. That's the action system. And I can move in two extreme modes. One is I can move in free space. It's called navigation. And the other, I can move through free space and I can interact with objects. So this is isotonic interactions. And this is isometric interactions, where where you've got a vertical line or a horizontal line. Force doesn't change, position does, or vice versa. So those are the two modes, and we have modes in between those. And that's simply the story of haptics told in 40 seconds. So all of haptics is about that. Most of our haptic devices are force actuated, and they're really bad at generating hard contacts. Why is it so hard to generate a hard contact? What's a hard contact? Well, it's a system. You can try to simulate it, but it's a system which, if you push on it with 1 Newton of force, what does it push back with? Yeah, 1 Newton of force. And if I increase to 3 Newtons of force, suddenly, what does it push back with? 3 Newtons of force. But how does it know? How does it know? How are you ever going to build a system like that? Well, you can build a position actuated system, but position actuated systems are lousy at allowing you to move in free space. So all these assistive devices, these glorious devices, Philip took us on a tour of Balgrist. They're well aware of that trade-off. You can only set up relationships between position and force. You cannot just command a force or command a position and have a usable system for playing in between those two. So we've got, if I'm trying to do this in a way which is not controversial, but it seems pretty controversial because it sounds like what I'm saying is that when you're interacting with these glorious human-computer interfaces, augmented reality systems, that all we can do, that bandwidth of information flowing from the computer to the human is matched only with this very low bandwidth output from humans, which is just about movement and position. Okay, but there's a saving grace in all this. If that's all that humans do, then we have the ability to measure their positions and their motions. The movement in that world, that we can be behaviorists. We can get data about the progression of the user's task by measuring the speed and accuracy with which they move through free space and select objects. And that can include error rates. If they're making decisions, that includes error rates and task time, or it involves speed and accuracy of their movement in free space. And I think I'm done with the stuff about what should be called evaluation. The user's performance can be evaluated objectively. Okay. So with that, I move on to the third one, which is now where, you know, I'm just going to speak like a professor, but this is going to be very controversial. The idea of validation. So what the hell is validation? What should it be? So let's come up to my keynote here. This is the slide. I have a whole deck. I mean, I have another 50 slides I could do on validation. But just like I did with cognitive biases, let's just pick on some common validities that we have. You'll see in the literature, people talk about face validity, content validity. You might see people say concurrent or predictive, but usually not. You'll see people say construct validity. So Nasir is already jumping in with some great questions. Let me just play this out. And I'm going to do this. I'm going to try to do this in a fun way. I've got 6 minutes left here. Hey, what does face validity mean? That's my dumb guy voice. Hey man, what is face validity? Anybody in the chat? I believe that there is a notion in our literature, surgical simulators and training devices, that face validity is how real did it look? And to try to argue against that common, I think it's common and I might be mistaken, right? You can all tell me, no, none of us believe this. This idea that realism is somehow face validity. That doesn't come from the literature of face validity. And I argue it this way. Let me invite you to join me in a Gedanken experiment where you have a virtual scene and that scene is rendered in very low resolution. That somehow that's got low face validity because what's facing us is low, I don't know. But as you begin to improve the rendering, you improve the resolution and you throw all kinds of innovations and come through all the glorious literature of computer graphics and rendering, illumination and baking scenes at Pixar. You know, you can make a lot more money doing that than you can making surgical simulators, I can tell you. That somehow, as you make the simulation more and more realistic, that somehow it has more and more face validity. But to argue against that, I'm going to give you this picture. Is this going to be okay, Sandrine? Look at that screen up there. Look at that glorious screen. How well rendered that surgical simulation is. This comes from a workshop Sandrine and I were involved with. It was called the Rookie Neurosurgical Boot Camp at CSTAR in London, Ontario. That I can ask you to join me in thinking about making that scene even more realistic and even more realistic until, in fact, it is one epsilon from being the patient. Now, in fact, this is pretty close to that because that's a cadaver. That's just an image taken from that cadaver head, which is also in the scene, okay? So now, if you're with me, if you kind of agree, all right, I'll give you that one, that you can make it look more realistic. My question is, in what sense is that cadaver's head a training tool? Could I ask somebody to come in and say, okay, that's really realistic, that now I'm getting trained. That you need to have the task on it, and you need to have the curriculum injected into this system. And that takes me to my next slide. Here is the injection of curriculum into training simulations. You'll notice that, in fact, in this synaptive device, so the synaptive user interface is up there on the wall. You see it there, and they have a phantom of a head. And nobody's looking at the screen. Nobody's looking at how realistic, how non-realistic is the phantom head. That, in fact, what was not in the cadaver and what is in this training simulation is content. Do I need to put some volume up? I'm not sure. This is our colleague, Dr. Andy Parent, a neurosurgical colleague of Sandrine's. Look, he's giving content. He's saying, look, here's what I want you to do. And it's about positioning the instrument and trying to find new approaches and reconcile things. It's got nothing to do with the realism of that. The question about face validity is, on the face of it, prima facie, does it seem like what is being taught here and what is being evaluated is a measure of what you're trying to teach? That's really what face validity means. And I guess as I come down 2 minutes to the end of this lecture here, we want to think about construct validity. What the hell is construct validity? Well, the question is really, what is a construct? What is a construct? A construct is a concept or an idea which has been made up of parts of things that you can measure. A geometrical example of a construct is here. If I have a tetrahedron, tetrahedron has vertices, has edges, has faces. These are objects. You can point at them, right? I can take the vertex and I can snip it off, and I have it in my hand. There's a vertex. But the construct, an example of a construct is its center of mass, right? There's a point in that tetrahedron, which is the center of mass, but it doesn't have that attribute on its own. It's not that you can go into that tetrahedron and measure center of massness of that. It's the quality. It's a construct. It's an idea. It is a function of the stuff that's outside. And you can come up with theories for how, on the basis of certain measures, you can come up with theories for what you mean by center of mass or moment of inertia. Navid Nawab had a great one at a wonderful restaurant meal that we had. He said, well, what about vortex? You know, if you're looking at water and there's a vortex in the water. And it really it gave me a lot of pause for a bit. But the idea that vortex is a system is not correct. A vortex is not a system. Vortex is a construct. I think there's a vortex. Now I can make measures, and I can make measures about flow, and I can think about the density of that. I can think about velocity and angular velocity, and I can come up with theories that there is a vortex there. And we can argue about whether or not the measures are valid measures of this construct, whether it be vortex or laminar flow. Laminar flow is another construct. We think there's this thing called laminar flow, and we have theories that suggest what we might measure, and we can argue about whether they're good representations of laminar flow or not. And hey, sir, what the hell does this have to do with augmented reality? Well, it has everything to do with augmented reality, because if you're using your augmented reality system to train people, then the construct is, have you injected surgical skill into that user? And you can't measure that. You can't measure whether surgical skill is now in the user. All you can do is measure their behavior. You give them a task to perform. You measure the speed and accuracy over well-defined tasks there. If it's diagnostic, the same thing happens. You give people tasks, you show them images, you ask them whether it's cancer or not, and you measure. their error rate and you measure their task time. And those are objective measures that evaluate their performance. But if you're trying to ask, I wonder if this system has injected diagnostic knowledge into that user, it's a glorious question because it's much more difficult. It comes from asking the question over and over and over again, just like in science. This is science again, where no one experiment will ever prove that the system has been validated. Systems don't get validated. The inferences that you make from measures can either be talked about as whether they are valid inferences or not. And that's what construct validity is. Have I done my job? I've tried to be as controversial as I can. It's supposed to be an innocent question. It's supposed to be an innocent topic. But now I hope I've set the stage for a panel discussion on, guess what? How do we validate AR? Do we have some chat questions, quick chat questions? Because we will try to work our way through these, but I suggest that we turn these chat questions into group questions, okay? Everybody take 5, have a bathroom break. We're gonna reassemble over here.
Roy, can I ask you just one question?
Nasir.
No, we were talking about time and accuracy as the only measures. Now, how should we deal with this fact that when we give AR system to our users, they have never used it, but what we compare to, they have used it all their life. So how is this evaluation fair in any kind of regards? So, I would like to evaluate an AR system in 2 years when they used it and they have the same habit of using it than what I'm comparing to. How can we fill this gap that we are giving them something and then we expect that to perform better than something that is based on their senses all their life? Now we add new senses to them and right away we want to compare with the other one.
Yeah.
So how should we do that?
Well, so there is, my message again, is that you can never say to somebody, how good is this AR? You can only do this. You can only say, for the following task, which you could do with AR or you could do without AR, let's see objectively whether it facilitates the task or not. Sometimes it doesn't, right? But it's tied to the task that user is performing.
My question, Roy, is that what if it would do if they work with it 6 months every day, but it would not do on the first day?
Well, that's a perfect usability question. Is that learnability of a system? I hope this isn't too controversial. Learnability is just quite simply your performance on a task with that system over time. And you better hope that the user's performance will improve over time. And you can get very quantitative learning curves about that system. And that allows you to start talking about whether that system was intuitive or not. Now, some systems are not intuitive, but in the hands of an expert through training, they can perform very sophisticated tasks with them. So it's a matter of looking at objective measures of performance over time. And that's a learning curve.
Thanks a lot, Roy. It was a great presentation. One last question. If I do the learning curve and look at the improvement of performance, how far am I allowed to extrapolate and predict what would happen in 6 months?
Usually there's a plateau. Most learning curves have an exponential function, which is associated with a plateau of skill. it's hard to imagine a task in which the more you do it, the better you get at it. There's always an exponential plateau. And Sandrine is just coming to the microphone with a question.
Thanks a lot, Roy. This was amazingly great. Thank you.
And Nasir, we couldn't have such great discussions like this if you didn't run this workshop every year except COVID.
Actually, Nasir, it's not a question. It's to answer your first question. I think one thing that we all tend to do, and I know you do it at your lab too, is instead of trying, if you want to prove that something is useful, instead of trying to put it in the hands of the expert, if you put it in the hands of novices or people in training, then it's going to be easier to show, because those people are less likely to have used the system for 30 years. And therefore, if you give them something new, and typically they are also more prone to using new technologies. So if you want to try to prove that your system is useful quickly, you need novices and early trainees to kind of show that they'll be better learning with that system. And then, yeah, sure, you could extrapolate and say, you know what, we can see that in early trainings and novices, they really benefit from it. Why don't we all use it clinically, and then you can do another test 6 months later? But for sure, it's going to be hard to show that experts are better using something that they've never used, even if that thing was way more performant than your previous tool.
And just to add to that, the usual scenario where you take a population of novices and they take a population of experts and you evaluate the performance in those two populations, you should be able to show a difference between experts and novices. Otherwise, if you don't, there was nothing that required domain knowledge. So you can set up experiments where you ask people to point at a tumor in a head. And you can find that novices are just as good at doing that as experts if you don't constrain it with things like avoid eloquent areas and such. So, you know, it's not really a test of expert domain knowledge. But if you do show that you've designed a task in which people with a certain qualification perform differently from people with another qualification, that's not construct validity, that's concurrent validity. That is, that your measure correlates with another measure, like their scores on their exams, you know, or what year they've made it through. So that really should be called concurrent validity. And if I can reach back to Eddie's question, what about surgical outcomes? That's predictive validity. Is that if you have a system which you hope will train clinicians to perform clinically, that the really important measure is just what Eddie said, that you want to have outcome measures. And that's very difficult to do. And that is where you try to establish predictive validity of your measures.
One question regarding phase validity. I think this is a simulator-specific validation. Do you have examples of this outside of the simulator field?
I sure do.
Could you please repeat the question?
Philip's, yeah, go ahead, Philip, if you want. Philip's question was about face validity.
I was asking about face validity. For me, I know it from the simulator field, there it is common. I was asking about examples outside of the simulator field for face validity.
So if I reach into the literature of validity and I come up with a statement of what is face validity is supposed to be prima facie, on the face of it, do experts believe that this test is a reasonable test of the thing we're trying to measure? That's face validity. And there are some great examples which you'll all forget my whole talk, but you won't forget these examples. An example of a test which has high face validity was the witch hammer. So there was a day when you wanted to test people to see if they're witches. And there was a hammer that you would use. And you would bash their knees. And if they would scream, then they were witches. That's a measuring tool. And now at that time, if you ask a set of experts whether that's a reasonable way to test for witches, at that time they said yes. So that ridiculous example is an example of at a particular point in time, witch hammers were thought to have high face validity. Now I'll give you another one, which you can pull out at a restaurant whenever you want. An example of a measuring device which has low face validity is a thermometer, you know, the kind. Because you say to yourself, well, how does this work? I want to measure temperature, and this thing is measuring height. And well, it's because height is a function of temperature. And you say, okay, but wait a second. You know, as that liquidy, watery stuff gets colder and freezes, it expands. This seems like a bad way to measure temperature, this device. So thermometers, unless you're an expert, actually have low face validity. Should not be a thing to measure temperature. There, you can count on me for a couple of restaurant jokes. But anyway, I don't make this shit up. If you Google that stuff, you'll see it. You know, this is classic stuff from literature. Okay, let's do what we promised. We will assemble into a panel because that's how we're going to end this keynote set. And you'll hear people who are much more expert in these areas than me, and we'll have a discussion because that's what it's all about. All right, take 5, everyone.